to understand flow and complete an experimental analysis of a magnetohydrodynamic fluid pump. So here's the old, really I should say the current. This is what a standard mechanical pump looks like. It brings water in with spinning mechanical blades and pushes it out. Now this works except for the mechanical forces wear this pump out over time, requires maintenance and additional parts. So here's the new. If you take two neodymium magnets in the red, you can create a magnetic field between them there. And you take the two electrodes in the blue, you fill the pump with a conductive fluid. In our case, we're going to use salt water. And you get a force called the Lorentz force, and it pushes on a fluid just in the same way that a mechanical pump would. So where is this helpful? In circumstances where you don't want to do maintenance, where it's a rough physical environment, and you don't want things to break. So one instance is desalination. As climate change continues to impact our planet, we're going to need new sources of clean water. So you can put an MHD pump at the bottom of the ocean. It works well with salt water and can move the system. The next place you really don't want things to break is space. So on the International Space Station right now, there's a series of mechanical pumps that are used for processing the fluid waste of astronauts. Now some call that urine, but essentially it's salt water. And so these pumps work for it. This is what our potential application is. We want to save astronauts time from having to do maintenance, and we save money having to send up replacement parts to replace the mechanical pumps. So here's how we're going to test it. This is called a CubeSat. It's a small experiment that can be set on a test flight into space. And my focus is just on what's within the apparatus itself, the experiment, the payload. We want to test this in space, but to justify a test in space, we really have to understand the flow here on Earth. So let's take a step back. Let's look at our foundational understanding. This is the Navier-Stokes equation. It's one of the governing equations of fluid dynamics. Essentially, it says that the motion here is equal to the sum of the forces. And we can make a couple of assumptions because this is an analytically unsolvable differential equation. So first, we can get rid of the pressure gradient term. We have a small system. There's not going to be gradients of the pressure. We can ignore. We can also ignore the viscous diffusion term because, again, we have a small system. Viscous diffusion is a force of result of the flow of the fluid itself, so we can ignore it. Also, if we're going to be testing in space, we can ignore gravity. So this looks a lot better, but it's still unsolvable. So we're going to do what's called a scaling analysis. We're going to look at what are the important parts of the forces and predict the velocity. So here we go. We say our velocity is going to be proportional to some scaling factor m. This has been experimentally determined for these types of systems, multiplied by information about the current and magnetic field of the pump and the geometry, the height, length, and width, and then subtracting from that the resistance to flow from gravity. The thing here is that resistance term actually dominates in the square root, and we know our flow is imaginary, we know our flow isn't imaginary, we know it's real, so we're going to ignore that term. Assuming there should be some scaling factor in there to make it physical, but this is what we're going to go for. The nice thing here is then we also get rid of that gravity term, so that means that our predictions here on Earth should line up pretty closely with our predictions for space. So what's the prediction? We're predicting about 2.5 centimeters per second of fluid flow, plus or minus 0.03 centimeters per second of uncertainty, given the uncertainty with our current and the concentration of fluid. So when I came into the Fab Lab, this was the testing apparatus. It used, I guess the video won't play. You can see it used food dye to test the flow through the system. And if the video would show it moves pretty slow, and also it's hard to get an accurate understanding of the flow from a wall of color moving forward. So we need to make a couple of improvements. One, I redesigned the pump. So essentially, I rotated the pump section here to be here. So the magnets go from being on the top and bottom to being on the sides. This maximizes the height, which in the scaled equation, we have height in the numerator, so we want to maximize that term. I also redesigned it a little bit so that the channel would provide better visibility for our testing. So that's our setup. Here's what it looks like in real life. It's a 3D printed pump. We have magnets, again, On the sides, the electrodes on the top and bottom, they're connected to a 10 volt power supply, providing about 0.15 amps of current. We have a GoPro that's positioned linearly over the top and aligned to ensure that it's directly in line with the pump. And we're using an 1130 kilogram per meter cubed density of saltwater solution. So this is analytically how we're going to get better information. We're going to use particle tracking. So these are individual particles from a company called Cospheric. They're neutrally buoyant, which means that they should flow exactly as the fluid flows. They shouldn't be impacted by the other forces. They're 1.25 grams per milliliter, and they're about 0.5 millimeter in size. That means that they're small enough, again, to not impact the flow, but big enough that we can observe them with our camera systems and distinguish the individual particles. And this is where we start to get some issues. You can see on the side and on the top here, there's some clumping of the particles. Now this isn't helpful because it means that the softwares are going to be tracking clumps instead of individual particles, which aren't going to be moving as we expect. You can also see at the top that there's some reflections from the room lights, and again, the analysis software we're using is going to be impacted by those reflections. It's not going to be able to see the particles in those reflections. Also, you can see that there's particles that are along the surface of the fluid, and fluid dynamics likes to be tricky, and so the fluid flow at the surface is going to be substantially different than the bulk fluid flow in the pump. So we're only, unfortunately, able to get one really usable trial during my time on this thesis. But what did we find? So with a technique called particle image velocimetry, PIV, you're here last week, you learned all about it. It compares particles' position across the whole system, frame to frame, and it outputs essentially a velocity heat map. It shows all of the velocity vectors for the thing, and here's what that looks like. So you can see we get some areas here that look like they have high flow, but they just are kind of recirculating along the surface in eddy currents. So as this video plays out, you would see that there would only be a little bit of velocity information here, but it's just sort of going in circles. In the empty areas, there's not enough particles for us to get consistent velocity information, and so it averages out to 0, which is entirely unhelpful. So better seeding would help with this, and different levels of concentration. So there's a different technique we can use. It's called Lagrangian particle tracking. Lagrangian particle tracking, instead of looking at the whole frame, tracks individual particles from frame to frame. So it outputs the magnitude of velocity for those particles. And what did we find? Well, using a program called LoggerPro 3, we tracked a particle from here to here. Now I know this looks like just a line, but it's actually a series of dots, one placed in every single frame to track the motion of the particle. And we found a magnitude of velocity of 2.52 centimeters per second. Now that's within our experimental uncertainty that we predicted. Now this is exciting for a couple of reasons. One, it means that Lagrangian particle tracking lines up with our expectations from the prediction. It also means that our predicted model is appropriate. That means in the scaling analysis, we didn't make too many assumptions and lose reality in it. So it also provides verification that our M value of 0.1 is appropriate for this situation and for these solutions. Now, this is great, but unfortunately we can't use LPT in space. It's a closed system. We only have one source of information for that. So this is a flow meter. It's from a company called Sensirion, and it'll be our only source of information in the CubeSat. This is our testing setup for it. It's connected to an Arduino, which is controlling it and getting the analog velocity information, flow information from the flow meter and outputting it. Unfortunately, we had some problems here. We have two different methods to try and verify that this pump is working as we expect, that it's reading the physical reality, and we had some problems. So just comparing the average expected velocity to the average of the values it collected, found 4.7 milliliters per second versus 0.2 milliliters per second. So not so good. We said, okay, maybe that didn't work, so let's try a different technique. Let's try looking at the total volume that went through. And comparing with trapezoidal numerical integration, the flow meter only measured 3.5 milliliters of flow compared to the 100 milliliters that were actually put through it. So clearly more work is required on this. We're thinking it's some issue with the code itself, but the company Sensirion hasn't responded to my emails or phone calls. I think they're ghosting me, I don't know what's going on. But future projects should be able to work on this. So what did I learn? One, experimentation is difficult. There's a lot of troubleshooting involved, from the lighting setups to getting particles to seed correctly, all this, there's a lot of problems. But we also learned that we have a strong foundation for further testing. Lagrangian particle tracking at the high level that we were now doing it does seem to be valid. It creates velocity information that we expect. And the PIV could be valuable if we had more seeding. So that's part of what's next. I'm going to try studying this system at different salinities, see if we can get better seeding at those different salinities, and also see what the impact is for having different concentrations of salt water, which will change how much current can flow through the system and the density of the system. So we'll see how that impacts the flow. We also want to, of course, get a better lighting setup with more diffuse, bright lighting that won't cause reflections, and then work to improve the flow meter, possibly with some folks in the electrical engineering department who speak Arduino a little better than I do. So where is this project going in the long term? Well, space. That's the long term though. To get there, we need to improve the control systems in the CubeSat. We need to get the flow meter to align with our experimental understandings. And then in the big picture, for MHD systems, we need to test them at different scales and different applications to see their potential for the future. Thank you.
So I know a lot of this research was based on space and how this can work in space, but another potential application you mentioned was a desalination. And I was just wondering if you did research on how that could be, how this pump could be practically applied to desalination, because like our current methods are like very, very high in CO2 emissions and very expensive, and oftentimes even require like a lot of government subsidies to even work competitively. So I was wondering if you did any research indicating how this could work to practically desalinate our oceans.
Yeah, so there's a patent that got filed a couple of years ago of a company that's trying to make a MHD desalination system. And it works to solve a lot of the problems you're talking about. It still would be pretty energy intensive. You still need the current to pump this system through. But using techniques like reverse osmosis, it would pump the salt water into the system and then allow it to continue through. It wasn't the folks in my thesis, so I don't know exactly how their setup works, but they seemed pretty excited about it.
When you did LPT, how did you go about selecting the particle that you used for the data?
I watched the video about 50 times and tried to find a particle that looked like it was in the bulk flow for the most amount of time and was moving in sort of the most consistent path. It was sort of an arbitrary thing. There's more complex LPT software that whoever's next could also start to implement that would track every single particle. So that would also be a technique. We could try different amounts of seeding. So try a lot more seeding for PIV and then less seeding for LPT to see if with less particles, computer software could find the velocity for every single particle. Yeah.
How did you choose the salination level of the water? Does the conductivity of the water change the Lorentz force? And did you select based on like similarity to the salination level of the ocean versus astronaut urine? I don't know what that analog would look like.
Yeah, so both the ocean and astronaut urine are pretty low amounts of salination. They're pretty low concentration of salt. We're using a much higher one because theoretically with more concentration, the density shouldn't impact it that much. It shouldn't raise that much, but we should get a lot more conductivity. So our current should be a lot higher and we should get more visible velocity flow. Also part of how we selected the concentration was trying a couple different ones and seeing where we could get good seeding with the particles, and where we wound up is what worked well.
Thank you, that was like super interesting. It sounds like one of the big impetuses for this is reducing sort of maintenance, but salt water and electricity is very corrosive. Do you have like a special material for the like electronic components? Are you using like sacrificial anodes, or what's the approach there?
Yeah, so the electrochemistry problem is a big problem. That's sort of the biggest issue for MHD systems. The way we were addressing it is with silver-plated copper electrodes. So the silver plating resists corrosion really well and extends the lifetime of the pumps for quite a bit. But yeah, I'll leave it to the rest of the people that work in this building to try and solve that electrochemistry issue. Thank you.
Thank you.